Square matrices. Under this topic, we try to learn about three important real square matrices: symmetric, skew symmetric, and orthogonal matrix. Then we try to generalize that for complex matrices, that is Hermitian, skew Hermitian, and unitary matrices. Before continuing that, we'll try to understand about transpose of the matrix. If you already know transpose, very good. Otherwise, quickly recap that. See, the transpose is also defined for non-square matrices. Not necessary for square, it is also defined for non-square matrices. Suppose you are having a matrix, say 3, 4, 5, 1, 2, 3. What is the transpose of the matrix? The transpose, see what is the order of A? 2 by 3. The transpose is obtained by converting rows into columns and columns into rows. So what is the first row? 3, 4, 5. That becomes first column, and second row becomes second column. That is, it becomes 3 by 2 matrix. If it is a square matrix, order will be the same. Okay, let us take 2, 1, 1, 4. Now what is the transpose of this matrix? So first row converted to first column and second row converted to second column. Oh, you again got the same matrix, and this is actually what is called as symmetric matrix. Similarly, we also define the other matrices, skew symmetric and orthogonal. Let us see one after the other. Definitions. A square matrix A is said to be symmetric if some condition is satisfied. What is the condition? The condition is the transpose of the matrix is same as matrix A. Means even after the transpose, you should get back the same matrix. So that is the definition of a symmetric matrix. See, under the definition I am writing this note. See, this note will help you in understanding how quickly you can verify whether it is symmetric matrix or not. And the note is this one. Aij is equal to Aji. This is the condition. The ith row jth column is same as jth row ith column. See, when you transpose a matrix, the ith row jth column will be converted to jth row ith column. Now, in symmetric matrix, what is happening? Transpose is same as matrix A. So what happens? The ith row jth column element will be same as jth row ith column. So this is the verification method for symmetric matrix. If I explain this with example, it will be more clear. Let us see the example. See, this is main diagonal. You can have any elements in main diagonal. But what about the off diagonal elements? This condition you verify. This condition will be satisfied. Suppose if you are having 4 here, you just imagine this as the main diagonal as the mirror. You can find a mirror image that should be exactly same as this. This is first row second column and this is second row first column. Both are same. Suppose if you are having say 6 here. So what is the mirror image? Here that would be 6. And suppose it is 5. This would be 5. See, if you just imagine the main diagonal as mirror, these two fellows are mirror images. That is it. Aij is equal to Aji. You can easily verify whether given matrix is symmetric or not with this method. I'll just quickly give you one more simple example to fix this idea. Suppose I given this matrix and I said that this is symmetric. You need to find A, B and C values. Of course, it's a very simple example. You can easily understand that. So symmetric means what? This is your mirror and these two elements must be same. Mirror images we call them. So the mirror images must be same. Hope you can answer this. What is A? 4. What is B? 5. What is C? 7. Done. And this is a very simple method to verify symmetric matrix. Okay, either you can use this general notation or you can just see this mirror images technique to understand symmetric matrix. Let us see the next definition. The next definition: a square matrix A is said to be skew symmetric. The previous one we call it as one symmetric, now it is skew symmetric if the following condition is satisfied. What is the condition? Transpose of A is minus A. This is the definition of skew symmetric matrix. How to verify a given matrix is skew symmetric matrix or not? See this note which I am giving, if you can understand this, you can very quickly verify the given matrix is symmetric or not or skew symmetric or not. Okay. Now skew symmetric means two conditions. First condition is the main diagonal elements are 0. All the main diagonal elements are 0. You want, you can just say all main diagonals. Okay. Second point, ith row jth column will be not AJI but minus AJI. So in the previous case we seen mirror images, right? Mirror images are equal, but in this case mirror images are having opposite signs. Let us see with example. Main diagonals will be 0. If it is skew symmetric, compulsory that is okay to be happening. Now this mirror images, this is 2 means you can just see the mirror images. This is your main diagonal. What is the mirror image? The mirror image must be minus 2, minus AJI. Suppose if it is 3, the mirror image is minus 3. Suppose if it is minus 4, the mirror image is plus 4. So you can easily verify whether the given matrix is skew symmetric or not. Okay, I'll just put it properly. Yeah. Okay. So this is how we can verify whether the given matrix is skew symmetric or not. Got it? Let us take one more simple example to fix the idea. Suppose A is, say A 2 minus 3, B 0, 6, C, D, E. He given this matrix and he is asking that, or he is telling you that it is a skew symmetric matrix. It is skew symmetric matrix. And he is asking you to find the values of A, B, C, D and E. Use the technique. First thing is what? If it is skew symmetric, main diagonals must be 0. Main diagonals must be 0. So what is A? 0. What is E? Also 0. These two are fixed. Now the mirror images, they should have opposite sign. So if it is 2, B should be minus 2. If it is minus 3, C should be plus 3. And if it is 6, D should be minus 6. So simple. Got it? A square matrix A is said to be orthogonal if the transpose of the matrix is inverse of the matrix. Okay? That is, the transpose will do the job of inverse of the matrix. See, normally A into A inverse, yeah, A inverse into A is equal to identity. But here The transpose itself is inverse. You don't have to find inverse. Even if you ask inverse, just find transpose. Convert rows into columns, columns into rows. You will directly get the answer. In GATE examination, they ask this question 2 to 3 times. They give an orthogonal matrix and they ask you to find inverse of the matrix. Okay, if you don't understand this basic property, you obviously waste your time in finding A inverse by adjoint A by dt property. Beautiful definition. Okay, and we also have a beautiful result to verify whether a given matrix is orthogonal or not. Okay, now let me tell you the result. A square matrix A is orthogonal if and only if its rows or columns, or let us say row vectors or column vectors, form an orthonormal set. Very, very important property. Let us try to understand this. Okay, see my dear friends, I'll explain with example, then you automatically understand this result. See, this is the matrix A cos theta minus sin theta, sin theta, cos theta. You want to check whether it is orthogonal or not. How to check whether it is orthogonal or not? One method is take A transpose, multiply them, and you should check whether it is identity or not. So please try at home whether this is satisfied or not. This into transpose. Transpose means cos theta minus sin theta, sin theta, cos theta. If you multiply, you should get 1 0 0 1. Please verify. I am not doing this verification. Now look here. What the property says is the following. If this matrix is orthogonal, the rows as well as columns, you can take any one. See, most of the time we are only worried about the columns in this case. So I am just explaining with columns. You can also verify with rows. See, the matrix, or the column matrix, if it is representing a vector, then it is called column vector. Similarly, row matrix also can represent a vector, then it is called row vector. So the idea is same. Okay, so this is first column, this is second column. Now you know the property orthonormal vectors. This is vector, column vector. What is length of this vector? Under root cos square theta plus minus sin theta whole square means sin square theta, which is 1. Similarly, what is length of y? Under root sin square theta plus cos square theta, which is also equal to 1. Now the dot product. Dot product means this vector and this vector, take dot product, cos theta into sin theta plus minus sin theta into cos theta, plus into minus, minus sin theta into cos theta. So what happened? 0. So the columns are forming orthonormal set. See, dot product is 0 means columns are orthogonal, and also the length of each vector is 1 means they are orthonormal. What the result says is, if the columns are forming orthonormal set, now clearly x and y are orthonormal, then automatically the matrix A becomes orthogonal matrix. See, please don't confuse with matrix and vector. For a matrix to become orthogonal, I repeat, for a matrix to become orthogonal, its columns must be orthonormal. That is the result. Hope you understand. Let us take the next example. It is a 3 by 3 matrix. Now I want to check whether it is orthogonal or not. Okay, you have to check like this. If you don't understand the property, you have to check like this. But what property says? X, Y and Z. The columns are forming orthonormal set. So you have to find length of each column. Okay. See, you don't have to write every time, sir. You know cos square theta plus sin square theta is 1. So length of x is 1. Length of y, sin square theta plus cos square theta 1. So under root 1 is 1. Length of z, 0 square plus 0 square plus 1 square. Under root 1 is 1. Directly length is 1. And dot product of any two vectors must be 0. So you take x dot y. You don't have to write separately. Directly you see cos theta into minus sin theta. That is minus sin theta cos theta plus sin theta cos theta. It is 0. Now take x dot z, x and z. Cos theta into 0, sin theta into 0, 0, 0 into 1, 0. Okay. What I do is I'll just show you with the colors so that you'll understand. This is what I done. That is 0. Okay. Now one more thing is y dot z. Let us see y dot z also. This into this. Okay, it's not visible. Let us use another color. Minus sin theta into 0, 0. Cos theta into 0, 0. 0 into 1, 0. So y dot z is also 0. Now all the three fellows are satisfying this condition. See, you need to take every two vectors, not just two vectors and satisfy. Now what happening? The columns are having length 1 and dot product of any two vectors is 0. See, you don't have to write entire steps. Directly from this you can easily verify this. So because x, y, z are orthonormal, that is the column vectors are orthonormal, that means the matrix is orthogonal. Now let us see the application of this property with one example. Now look at this example. This particular matrix is given as orthogonal. He says that this matrix is orthogonal and he is asking you to find alpha and beta. So in this case you don't have to verify whether it is orthogonal or not. You know it is orthogonal. You have to find alpha and beta. Suppose if you don't know this property which we just discussed, then you have to check like A into A transpose is identity and verify. But using the property we can get the answer very quickly. You call it as x, you call it second column as y, you call third column as z. You don't have to do completely, sir. Just use any of the properties. See, columns must be orthogonal because matrix is orthogonal means x, y and z are orthonormal. So if matrix is orthogonal, its columns are orthonormal. I just use the property. Because I just need to find alpha and beta, what I do is I just do x dot y. X dot y means, see, I just need to multiply this. I'll just show you again. This into this, this into this, this into this. But if you observe, the denominator is common. 9 into 9 is 81. Denominator is 81. Numerator minus 4 plus 32 minus 7 alpha. But orthonormal means x dot y must be 0. And if you simplify this, it is 28 minus 7 alpha. 28 minus 7 alpha is, because 81 into 0 is 0. That means 7 alpha is 28. Yani alpha is 28 by 7, that is 4. Now to get beta, just do y dot z. Again you have to multiply these two. This into this, this into this, this into this. So denominator is 81. Numerator minus 32 plus 4 minus 7 beta, that must be 0. 81 into 0 is 0. So you get minus 28 minus 7 beta is 0. That means beta is 28 by minus 7, that is minus 4. And you got the answer within no time. But wait, there is a small mistake which people do. I just want you to understand that. Okay, answer is ready, but I just want you to understand people do in a different way and they get different answer and they are worried about it. So what is that? Let us understand. Now if you see the first column, 1 by 9, 8 by 9, alpha by 9. See, this is x vector. If you just see the vector x, this is x vector. So when you say orthonormal means mod x square, you have to do it. Mod x square means, okay, denominator is 81. It is 1 plus 64 plus alpha square. And mod x square is how much? 1. Now if you simplify this, it is 65 plus alpha square is equal to 81. So that is alpha square is equal to 16. So people feel alpha value should be plus minus 4. Then why you should take plus 4 only? This is the doubt people get. See, my dear friends. See, this alpha value should satisfy both the condition. It should satisfy mod x is equal to 1 and x dot y is equal to 0. Both the conditions must be satisfied. Which value of alpha satisfy both the condition? See, alpha is equal to plus 4 satisfy this condition and this condition. But alpha is equal to minus 4 only satisfy first condition but does not satisfy the second condition. So we don't take alpha minus 4, we take only alpha is equal to plus 4. So this is the doubt which people get. So this is the solution for that. Is that clear? Like that. Now let us generalize the same idea for complex matrices. First of all, understand what is complex matrix. Then we try to give the generalized definition for symmetric, skew symmetric and orthogonal matrices. What is a complex matrix? Simply, a complex matrix is one whose elements are complex numbers. Now you may feel why 7? See, every real number is a complex number because 7 plus I0 you can write it. Okay, like that. Now what is conjugate of this? The conjugate means replace every element by conjugate. For example, a plus ib is a complex number. Its conjugate is, what is the conjugate? A minus ib. So just replace every fellow with its conjugate. So 3 minus 5i, 2 plus I, and imaginary part sign will be different. And if it is a real number, conjugate will be exactly same as original number. Wonderful. Now what is conjugate transpose? What is conjugate transpose? See, conjugate transpose means after conjugate you have to transpose it. So some people write, other notation. They also call it as tranjugate. They use the notation a theta. But this is a better notation, conjugate transpose. Okay. See, after conjugate you have to transpose the matrix. So transpose, you all know it, right? Convert column to row. So this information, if you know, we can continue with the definitions for complex square matrices. 3 important complex square matrices. Let us see. Definition. A complex square matrix A is said to be Hermitian Okay, first definition for complex matrices: if the conjugate transpose of the matrix is equal to matrix A. Conjugate transpose of the matrix is equal to matrix A. Now, before continuing further, I'll just tell you one simple thing, then I'll continue with the definition. Suppose if the matrix is say 3, 4, 4, 8, it's a real matrix. What is conjugate of it? Conjugate would be 3, 4, 4, 8 only. So if it is a real matrix, the conjugate would be same as matrix only. So instead of complex, if you are taken as real matrix, what happens to this definition? Because conjugate becomes A only. This definition is simply A transpose is A. Is it clear? That means this definition becomes definition of a symmetric matrix. What do you mean by that? Symmetric matrix is a special case of Hermitian matrix. Now we are defining a more general matrices. That is the idea. So the symmetric matrix which we studied is a special case of Hermitian matrix. Okay? Like that. If it is complex matrix, you have to find conjugate transpose, that would be A. But please remember the simple method which I give you now. Notes. These are the points with which you can quickly verify whether the given matrix is Hermitian or not. The first point for Hermitian matrix is all main diagonal elements. All main diagonal elements are real numbers. Main diagonal elements are real numbers. Second thing which we need to understand is the ith row jth column element is equal to, see, for symmetric it is aij is equal to aji, but here aij is equal to conjugate of aji. Okay, see, with this points I'll construct a Hermitian matrix so that next time onwards whenever he gives Hermitian you can easily identify. See, Hermitian is used in a property of eigenvalues and eigenvectors. Of course, complex matrices are very interesting, but for our examination they are only for understanding a property of eigenvalues and eigenvectors. Clear? Now look here. Let us construct a Hermitian matrix on our own. For a Hermitian matrix, the main diagonal must be real numbers. You can take any real numbers. 2, minus 5, 7. You can take any fractional values also, no problem. Now what is the next thing? This is your main diagonal. This is your main diagonal. The second property also you can easily understand here. The second property also you can easily understand. What is it? Aij is equal to conjugate of aji. That is, if you are having 2 plus I here, then the mirror image would be its conjugate. And what is that? Just write 2 minus I. You all know conjugate. Just write that. Suppose if it is 3 minus 2i, what happens to its mirror image? The mirror image would be here, and what is that? 3 plus 2i. Just write conjugate. And suppose if it is say 2i, or you can take 4i, whatever number, 4i, then what is this number? Minus 4i. And you can easily verify whether it is a Hermitian matrix or not. First condition, check all the main diagonal elements. They must be real numbers. And these two fellows must be conjugates of each other. You all know conjugate means one is a plus ib means the other fellow must be a minus ib. And with this we can very quickly verify whether the given matrix is Hermitian or not. Clear? Like that. Let us see the next definition. A complex square matrix A is said to be skew Hermitian if the conjugate transpose of this matrix is equal to minus of the matrix. And if you observe, this is a general case of skew symmetric matrix. That is, skew symmetric matrix is a special case of skew Hermitian matrix. Because if A is a real matrix, it simply becomes A conjugate will be A transpose will be A minus A. Therefore, skew symmetric is a special case of skew Hermitian matrix. Got it? Now the note. The first point is the main diagonal elements for a skew Hermitian matrix. The main diagonal elements are either pure imaginary or 0. See, for skew symmetric matrix, main diagonals must be 0. But for skew Hermitian, main diagonals must be either pure imaginary or 0. And the second condition is Aij is equal to minus Aji conjugate. Aij is minus Aji conjugate. See, this is very interesting to understand, sir. For example, one fellow is 2 plus 3i. Conjugate means 2 minus 3i. Minus conjugate means minus of 2 minus 3i. Sorry. And what is minus of 2 minus 3? 2 plus, sorry, minus 2 plus 3i. So, if it is minus of conjugate means the real part sign would be different, whereas imaginary part sign is same. Conjugate means imaginary part sign is different. Minus conjugate means real part sign must be different. Simple. Now let us take one example to, or let us create one skew symmetric matrix. See, if you can create skew symmetric matrix on our own, we can easily identify. Got it? What must be main diagonal elements? 0 or pure imaginary. 2i, 0, 3i. Works. Next, if you take main diagonal as mirror, the mirror images must be minus conjugates of each other. That is, if one of the element is say 2 plus 3i, what must be its mirror image? Real part sign must be same. Oh, sorry. Real part sign must be different. Imaginary part sign must be same because it is minus conjugate. Okay, that is what I said. 2 plus 3i means it is minus 2 plus 3i. Again, take the next number. Just extend this. Now, say minus 4 plus I. So, what must be its mirror image? The mirror image will be here. What must be that mirror image, fellow? It must be real part sign must be different. 4. Imaginary part sign must be same. Got it? Suppose if I put 3i here, then what must be this number? This is here, na? The mirror image. The mirror image would be here. Okay. So, imaginary part sign would be same. Real part sign would be different. So, if you are confused with both 3i's, you can just take different number here. I'll just make call 4. Let us call it as 4. Okay. And this would also be 4. Okay. Right here. So that it looks like a matrix. Got it? Hope you understand. It's a very simple property. Okay. Let us take the next definition. Third definition. A complex square matrix A is said to be unitary if the conjugate transpose is equal to A inverse. See, if you studied the definitions for real matrices, you can easily remember this definition also. Just in place of A, you get conjugate. That is the story. So, what is the story here? A multiplied with its conjugate transpose or A conjugate transpose multiplied with A will give you identity. This is the idea. As I told you now, some people use this A theta notation instead of writing conjugate transpose. They call it as tranjugate also. That is their wish. Okay, you also can follow that particular notation if you like. It's just a notation, nothing more than that. Okay, now let us take example. We don't have any special rules for this. The rules are there, but they are involved. We are not very much interested in complex matrices to that level. We are learning to a basic level which is needed for our examination. So I am just giving you the general example for this. A is, you can try this example, 1 by root 2, I by root 2, I by root 2, 1 by root 2. Now conjugate transpose, you take conjugate. Conjugate means, okay, for real numbers no change, but for imaginary numbers sign will be changing. I by minus I by root 2, this is also minus I by root 2. And what happens to conjugate transpose? 1 by root 2, actually it is same fellow only. 1 by root 2 minus I by root 2 minus I by root 2, 1 by root 2. Okay, sorry. What I want you to do is just multiply these two matrices. A multiply with A conjugate transpose. 1 by root 2, I by root 2, I by root 2, 1 by root 2. Multiply with conjugate transpose. 1 by root 2 minus I by root 2 minus I by root 2, 1 by root 2. And you all know this, I square is minus 1. Using this, you can multiply and get the answer. Or let us quickly solve this. 1 by root 2 into 1 by root 2 is 1 by 2. I square minus 1, but minus I square means plus 1. Plus 1 by 2. Minus I by 2 plus I by 2, 0. I by 2 minus I by 2, 0. And I square minus I square means this into this. Minus I square means plus 1 by 2 plus 1 by 2. So you got the answer 1, 0, 0, 1. So the given matrix A is unitary matrix. This is unitary matrix. See, other square matrices like upper triangular, lower triangular, diagonal matrices, we try to see together with determinant properties. Okay, we don't have to spend separate time for them. We can understand those definitions with the concepts of determinant, properties of determinant. Okay, now let us quickly understand the elementary row operations. The following three are called elementary row operations. The first one is interchanging two rows. So we denote it symbolically like this, Ri interchanged with Rj. Instead of writing this big statement, we can simply remember like this, Ri interchanged with Rj. So we use the two-sided arrow to show that. Suppose you want to interchange R1 with R2, you can write R1 two-sided arrow R2. That is interchanged with R2, swapped. Second one is multiply a row with a non-zero constant. This should be a non-zero constant. So you write like Ri is k times of Ri. And the third one is adding a constant multiple of other row. I'll write here Ri is Ri plus k times Rj. That is k times of Rj is added to Ri. These three are called elementary row operations. I'll explain with example. Before continuing further, I quickly tell you what are these elementary column operations. The first one is interchanging two columns, multiply a column with a non-zero constant, adding a constant multiple of other row to a given, other column, adding a constant multiple of other column to a given column. Okay, these are elementary column operations similar to elementary row operation. But I try to avoid these elementary column operations as much as possible in this particular course. Okay, because most of the course require only elementary row operations. Okay, some parts we can also apply column operations, but I tell you how to do without using column operations for those problems also. Okay, so let us quickly understand with one example these elementary row operations. I am only giving you row operations. Okay, 4 2 1 2 1 3 3 2 1, some 3 by 3 matrix. I quickly tell you the different row operations on this. Now what I do is I want to interchange R1 with R2, means swap R1 with R2. So what happens? The second row becomes the first row and first row becomes the second row. Rest of the story same, no change. See, this new matrix is not matrix A, it is some other matrix. Okay, so I not put equal to the symbol we use for that new matrix. Okay, now on this I want to perform, this is the first type of row operation. Let us understand second type of row operation with example. What I do is I multiply R2 with 2. Simple, you can multiply with any number. I am just showing you one example. So you get a new matrix. Again, this new matrix is not same as the previous one or A, it is new matrix. So first row is same, second row 4 2's 8, 2 2's 4. Every element of the row to be multiplied with 2. 1 into 2 is 2. So it is 3 2 1. Got it? Now let us see a third row operation. This time I use this third row operation for a purpose. Using this element, I want to make this element 0. Third type of row operation. So what I do, R2 is R2 minus 4 times of R1. See, actually, R2 is R2 plus minus 4 times of R1 also you can write. Constant times of other row is added to this row. You got the meaning? Like that. Anything is fine. Plus into minus 4 times of R1 you can write it. Okay, now what happens? See, first row I am using it, it is same, but now second row changes. 8 minus 8, 0. 4 minus 2, 4 minus 4, 0. Wow. 2 minus 12, minus 10. Like that. But the third row is same, 3, 2, 1. Like that. So what I want you to do is try one more row operation because all are done. Using this element, make this element equal to 0. Now here I will tell you two ideas. Let us take next slide to make this more clear. 2 1 3 0 0 minus 10 3 2 1. Now look here. Using this you want to make this element equal to 0. See, if you want to go with strictly row operations which are available, that is interchanging two rows or multiplying a row with a non-zero constant or adding a constant multiple of other row, if you want to make R3 this element 0, so the question answer would be R3 minus 3 by 2 times R1. That is a strict row operation. But for manual applications, working with factors would be boring or difficult or tedious, you can say anything. So generally when you do manual row operations, we try to make some modifications. We try to combine two row operations. For example, what I do is I do this R3 is you multiply this 2 here and you multiply this 3 here. That is 2 times of R3 minus 3 times of R1. So we are working with integers. So there is a method called Gaussian elimination. Actually, strictly speaking, you have to use this type of row operations only. But manually when you are doing, we make some, okay, proper simplifications like this, or we make, combination of row operations, so that we will not have that difficulty working with fractions. That is allowed. Got it? Like that. So now you got a new matrix. First row as it is, second row as it is, third row changes. See here, this one I am using. You can try this also, but as I told you, we try to avoid working with fractions manually when you are doing. Okay. Generally, computer programs which I use Gaussian elimination methods, which always use this row operation only, strict row operations only they use. Got it? Like that. Now this is 3 to 6 minus 6. Obviously, this is 0. 2 to 4 minus 3, that is 1. And it is 2 minus 9 minus 7. Okay. Even though I not given you a proper story, this is the purpose for using this row operation. To make certain elements zeros, we use this, mostly the third type of row operation, which is very, very useful. Please remember.